Swayam Prabha. Digital India. Educated India.
Good morning. I'll continue the discussion on gas turbine cycle analysis and jet propulsions. Content of the lecture are jet propulsion. Under jet propulsion, I'll discuss today propelling nozzle. So the nozzle loss for the unchoked flow and for the choked condition. And then I'll discuss on the propulsive ducts. I'll derive the expression for thrust, propulsive efficiency, thermal efficiency, and the overall efficiency. I'll discuss now about the propelling nozzle. The term propelling nozzle is referred to the component in which the working fluid expanded to produce a high velocity jet. In a turbojet engine, there exists a nozzle downstream of the turbine producing thrust. Often, an afterburner is introduced for thrust boosting, where the jet is further reheated. Now, the net thrust can be assumed as the sum of momentum thrust and pressure thrust, which can be expressed as F is equal to M into Cj minus Ca plus Aj into Pj minus Pa. The first bracketed term represents the momentum thrust and the later one is the pressure thrust. Now here, the aircraft is flying with a uniform speed Ca and Cj be the speed of jet velocity. Similarly, Pj is the pressure at the plane exit of the propelling nozzle, while Pa is the atmospheric pressure, and M is the mass through the engine, mass of air, or in this case actually it would be the mass of gas, and Aj is the effective area of the nozzle. Now further I'd like to tell you that the design of a propelling nozzle depends on the operating condition of the flight. Thus, the question immediately arises as whether a simple convergent nozzle is adequate or whether a convergent divergent nozzle should be incorporated particularly for supersonic flow. Here, let me assume the critical pressure BPC. Thus, the critical pressure ratio can be estimated assuming isentropic flow while gamma being 1.33 as P04 by Pc is equal to gamma plus 1 divided by 2 to the power gamma by gamma minus 1, that lead to 1.853. So this relations will give me the value of critical pressure. Now if P04 by Pa is less than P04 by Pc, that means if atmospheric pressure is greater than critical pressure, which is the condition for unchoked flow, then the flow is subsonic in the propelling nozzle. Further, if P04 by PA is greater than P04 by PC, which is the condition for choked flow, then the velocity could be potentially supersonic depending the use of a convergent divergent nozzle. However, the use of convergent divergent nozzle is avoided as it would result in significant increase of engine weight, length, diameter, and thus the aerodynamic loss. So thus, please note here that even the atmospheric pressure is less than the critical pressure, we generally use the convergent nozzle, considering the fact the use of a convergent nozzle would create significant aerodynamic loss, engine weight, and length. Let me conclude here that a convergent nozzle is used up to a limit when P04 by PA is less than or equal to 3.0. Now, suddenly for P04 by PA is greater than P04 by PC, that means when atmospheric pressure is less than the critical pressure, an isentropic expansion produces the maximum thrust when the gas would be completely expanded to the atmospheric pressure in the nozzle. However, in an incomplete expansion, loss in thrust would be partially compensated by generation of pressure thrust, that is AJ into P5 minus PA, because here P5 would be greater than PA. Now, the nozzle laws for the choked and unchoked flow would be discussed in the following page. I'll discuss now the nozzle laws for the unchoked flow. That means when P04 by PA is less than P04 by PC, that means atmospheric pressure is greater than the critical pressure. Now, the real and isentropic expansion of gas that's occurring in the propelling nozzle has been illustrated in the TS diagram by figure 16, where 04 is the pressure and temperature at the exit of the turbine. So I have indicated here the state point 04 in TS diagram and P04. And 04 to 5, which has been shown by the dotted line, is an actual expansion of gas that's occurring in the nozzle. And this is the non-isentropic process, so entropy has increased. And 04 to 5 dash is the isentropic expansion in the nozzle. So P5 is equal to the atmospheric pressure. Note that the difference between T04 and T5 can be equated with C5, that is C5 squared divided by twice Cp. Again, T04 is equal to T05, and thereby I can get P05, which has been expressed here. Now I have drawn the 3S diagram. After drawing the 3S diagram and getting the state points, I can now write down the expression that is T04 is equal to T05, that is equal to T5 plus C5 squared divided by twice Cp. And the pressure ratio P04 by Pa can be related with the temperature ratio T04 by T5 dash. Thus P04 by Pa is equal to T04 by T5 dash to the power gamma by gamma minus 1. Now here P5 must be equal to atmospheric pressure Pa, which is higher than the critical pressure Pc. Now let me define the isentropic efficiency of the nozzle, which can be expressed as eta J equal to T04 minus T5, actual temperature drop in the nozzle divided by isentropic temperature drop, that is T04 minus T5 dash. Here you see, look in the TS diagram, this is T04 and T5, this is T04 and T5 dash. So after definition of the nozzle efficiency, I can go ahead further. Now for a given inlet condition P04 and T04, and also with an assumed value of nozzle efficiency eta J, we can evaluate T5 following that T04 minus T5 is equal to eta J into T04 within the bracket 1 minus T5 dash divided by T04. Now T5 dash by T04 can be related with pressure ratio, as you can appreciate from TS diagram. Further, we know T04 minus T5 is equal to C5 squared divided by twice Cp. Thus we can write that eta J T04 within bracket 1 minus within bracket 1 divided by P04 by Pa to the power gamma minus 1 divided by gamma equal to C5 squared by twice Cp. Thus, I can evaluate the pressure ratio Pa by P04 as equal to 1 plus 1 by eta J into C5 squared divided by 2 Cp into T04 to the power gamma by gamma minus 1. Therefore, I can relate C5 with respect to pressure ratio for a given value of eta J. Under this condition, pressure thus would be equal to 0 as P5 here is equal to Pa. Now I'll discuss the nozzle loss for the choked condition. Now here the atmospheric pressure Pa is less than critical pressure Pc, and thus the nozzle will be choked, and P5 remains at the critical value Pc, and thus C5 remains at the sonic value, which is equal to root over gamma R into Tc. With this understanding, I have drawn the expansions of the gas in the nozzle when the flow is choked in figure 17, that's a TS diagram, for the condition when P04 by Pa is greater than P04 by Pc. That means the atmospheric pressure is less than the critical pressure. Here look, 04 is the state point at the exit of the turbine. So P04 to C, which has been shown by the dotted line, is the expansion of gas when the nozzle is choked, where at the exit of the nozzle the pressure is Pc, temperature is Tc, and the speed of the jet is equal to root over gamma r into Tc. Now the T04, which is equal to T05, can be related with Tc by C5. That means what I like to say that T04 minus Tc is equal to C5 square divided by 2ICP. Now look, I have denoted here this actual expansion, isentropic expansion, and the corresponding state points. After that, the outstanding questions is how the critical pressure could be evaluated for the non-isentropic expansion of gas in the nozzle. To do that, I can write T04 by T5 is equal to T05 by T5 is equal to 1 plus C5 squared divided by 2ICP into T5. That can be written as 1 plus gamma minus 1 by 2 into M5 squared. Now put M5 is equal to 1. Then I can write T04 by T5 is equal to gamma plus 1 by 2. Look here, T5 is equal to Tc. Having found Tc, the question is that how can I evaluate Pc? To do that, I'll have to assess Tc dash from the definition of efficiency of nozzle, eta J. Now, the efficiency of the nozzle can be defined as eta J is equal to T04 minus Tc divided by T04 minus Tc dash, referring back to the TS diagram. Now, from this expression, I can write Tc dash. Tc dash equal to T04 minus 1 by eta J into T04 minus Tc. Now, look in the TS diagram, 04 and C is the isentropic expansion. So, Pc can be related as Pc is equal to P04 into Tc dash by T04 to the power gamma into gamma minus 1. Now, Tc dash and T04 can be related with eta J, that is nozzle efficiency. Thereby, I can write Pc is equal to P04 within the bracket 1 minus 1 by eta J into 1 minus Tc by T04 to the power gamma by gamma minus 1. Now, substituting the value of T04 by Tc is equal to gamma plus 1 by 2, we have Pc by P04 is equal to, within the bracket, 1 minus 1 divided by eta J into gamma minus 1 divided by gamma plus 1 to the power gamma by gamma minus 1. So this is an important relation which give me the value of PC. Now look here, the PC has been related with gamma and eta j. Under this condition, the pressure thrust would be Fp is equal to Aj, area of the nozzle, into Pj minus Pa. Note that Pj would be greater than the atmospheric pressure Pa. Thus, here the total thrust would be summation of momentum thrust plus the pressure thrust. Thus, F equal to M into Cj minus Ca plus Aj into Pj minus Pa, where Pj is equal to Pc, Cj is equal to Cc is equal to root over gamma R into Tc, and rho c is equal to Pc divided by R into Tc. Now, for a given mass flow rate M, the area of the nozzle A5, that is equal to Aj, would be equal to M divided by rho c into Cc. Cc must be equal to Cj, that is equal to root over gamma R into Tj. Now, here I like to state that the nozzle efficiency depends on the operating conditions. However, for cycle calculation, we may assume the nozzle efficiency as 0.95. I'll now discuss about the propulsive duct. Let me consider first an aircraft flying with a uniform speed Ca and Cj be the speed of jet velocity. Similarly, Pj is the pressure at a exit plane of the propelling nozzle, while Pa is the atmospheric pressure. Now, a propulsive duct, as indicated in figure 18, is a schematic of a jet engine. Relative to the propulsive duct, here entails the duct with a uniform speed Ca and lives with a jet speed Cj, as indicated here in the figure 18. Thus, the net thrust can be assumed as the sum of the momentum thrust and the pressure thrust, as indicated earlier. Here Pj is greater than Pa, and thus thrust T can be stated as M into Cj minus Ca, which is equal to momentum thrust plus Aj into Pj minus Pa, that's the pressure thrust. When an aircraft is flying with a uniform speed, thrust must be equal and opposite to the drag on the craft. Further, if we ignore the pressure thrust, then the thrust per unit mass flow rate can be expressed as T is equal to Cj minus Ca. Now in this case, I have assumed the fuel air ratio is small. Now, the thrust per unit mass flow rate will be maximum when Ca is equal to 0. From this expression, we can understand. And this maximum thrust when Ca is equal to 0 is referred as the static thrust. Thrust power is the rate of useful work done by the engine per unit mass flow rate. and is given by Tp is equal to T into Ca, that is equal to Cj minus Ca into Ca. Now the propulsive power is obtained from the change in kinetic energy between the incoming air and the exhaust gases. Thus, for unit mass flow rate, the propulsive power is defined as Pp equal to Cj squared minus Ca squared divided by 2. Now, if the fuel-air ratio is taken into account, then Pp is equal to 1 plus F into Cj squared minus Ca squared divided by 2. Now, the propulsive efficiency can be defined as eta P is equal to thrust power divided by propulsive power. So, eta P is equal to Cj minus Ca into Ca over within bracket Cj squared minus Ca squared divided by 2. This can be simplified as eta P equal to 2 sigma divided by 1 plus sigma, where sigma is the ratio of Ca by Cj. Now, the thermal efficiency can be defined as eta thermal is equal to propulsive power divided by rate of heat supplied in the combustion chamber. So, eta thermal is equal to Cj square minus Ca square divided by 2 into 803 minus 802. 803 minus 802 is equal to change of enthalpy while heat is being supplied. Now, the overall efficiency based on the caloric value of the fuel can be assessed at eta OF is equal to thrust power divided by fuel air ratio into calorific value of the fuel. Thus, we can express as eta OF is equal to eta P into eta thermal into eta B, where eta OF is the overall efficiency based on the calorific value of fuel, eta P is the propulsive efficiency, eta thermal is the thermal efficiency, and eta B is the combustion efficiency. For the jet engine, the fuel consumption is expressed as the specific fuel consumption, which is the ratio of fuel consumed per hour to the specific thrust. Thus, the specific fuel consumption can be expressed as SFC equal to 3600 F divided by TS, where TS being the specific thrust, which can be expressed as T divided by ME, where ME being the mass flow rate. Here, F is the fuel air ratio, and the unit of specific fuel consumption would be kg per Newton hour. Thank you for listening.